Hello and welcome to another Arlington High School Math 4 Honors lesson. My name is Kirk Weiler and today we're going to be doing unit number 11, lesson number 1, Major Derivative Theorems. So unit number 11 in this course is one of the final units, and there's some wrap-up work, some applications of derivatives that we haven't looked at. And one of the things that we need to examine are some of the major theorems that are lying in the background of calculus and are used in later calculus courses, but which can be understood using pretty much the calculus of a single variable. A lot of these theorems have names associated with them, and names that you kind of want to know because then you can kind of cite those names, or you can watch for those names both in future calculus courses and on the AP exam. So let's launch into them and let's take a look at the first major theorem. Alright, we're going to actually do this through the context of an exercise. One of the things that I want my students to be able to do is I want them to be able to read the technical language of a mathematical theorem. It is often very confusing looking, very strange looking. Fortunately for them, this is actually one we've done already. But if you're not in my course, you might look at this and say, what does this theorem even mean? So I'd like you to pause the video, read through the theorem, and then try to figure out the answer to that question. If you don't know the answer to the second question, in other words, what is the technical name for the theorem, don't worry about it. Anyway, pause the video now. Okay, let's take a look. Reading mathematics is something that takes a lot of practice. It's good to really work at it. For mathematicians, when they read something in mathematics, it's almost like a beautiful language because it cuts through all ambiguity. You know, it's just logical and it makes all the sense in the world. So when I read this, let's take a look. It says, given that the function f of x is continuous, but not necessarily differentiable. Now immediately you hopefully have an idea of what both of those two things mean. All right? Continuous, meaning that you can't have any breaks, jumps, skips, there's no vertical asymptotes, there's no steps, there's no holes. You can't have any of that on a closed interval, a to b, so the endpoints are included. Not differentiable, right? Differentiable means smooth. No corners, no discontinuities, no vertical tangent lines. Anyhow, let's take a look at what it says. It says, given that f of x is continuous, there exists a c, okay, such that c is bigger than a, but smaller than b. So in other words, c is somewhere in this interval. It could be a, or it could be b, but it's somewhere in that interval. So there's some c such that c is in between a and b, and f of c is greater than or equal to, right, f of x for all x in a and b. And then number 2, it's kind of like everything, but there's less than or equal to. So what does this theorem guarantee? Well, what I always tell my students is to first really understand what each letter represents. Does it represent an input, an x value? Does it represent an output, a y value? So it's really important to understand C. C is some specific input. It's an x value, right? So here I've got some function, right, on a to b. All right, it's continuous. It's not necessarily smooth, so I'm going to throw in a corner. But there's no holes, anything like that. Now there exists a c, so there's a c somewhere in here. I don't know where. Such that f of c, what's f of c? F of c is an output. Specifically, the output at x equals c, right? So it's a y value. What do we know about that? That y value is greater than or equal to, well, what's f of x? This is a generic y value, a generic output, right? It's f of x, where we don't specify x, for all x in a and b. So there's some x that gives us a y such that the y value at that x value is greater than or equal to the y value at any other x value. Actually, that even includes x equals c. So, yeah, there is a y value that is bigger than all the rest. So what this theorem is really, whoops, sorry about that. I don't know what just happened there. I suddenly got out of keynote. That was weird. Whatever. So what this theorem is saying, at least number one is saying, is there exists an x value that gives us a largest y value. There's an x value that gives us the largest y value, as long as the function is continuous. You see, if we have a discontinuous function, if we have something like this, let's say we've got a and b, and actually make that look like a b, you could have a scenario like this, right? So one would think that this would be y max, except there's a hole in it, right? And what are you going to do? You can look at the vertical asymptote case as well. That's a very, very good point, right? If you looked at something like y equals 1 over x, right? Let's actually put some arbitrary interval. Let's say we go -2 to 2, right? There is absolutely no x value in the interval -2 to 2 where you get the largest y value. There just isn't, right? It's not x equals 0 because you can't even get a y value at x equals 0. Number two in this theorem just basically is the minimum case, right? So there exists an x value, a specific x value, where the y value is smaller than all other y values. This theorem does have a technical name. Here, I'll put it in green. This is the absolute min-max theorem. It's a theorem that guarantees us, if we have a continuous function on a closed interval, that there will be an x value that gives you the largest y value, and there will be an x value that gives you the smallest y value. Okay. Doesn't mean there can't be ties, all right? Anyway, we're going to clear this out, and then we're going to go on to another one of our major theorems. All right, so take a look. Ooh, lots of colors. All right, let's move on. I'm going to grab a little drink of water. It's a little bit dry today. Thank you. All right, so in the next exercise, we're going to look at something called Rolle's theorem. So Rolle's theorem, Michel Rolle, I think it is, French, got lucky because he got to put his name on a theorem that will probably seem pretty obvious to you and is an amazingly important theorem. All right, so let's take a look. In exercise 2, we're now given a differentiable function. Now again, it's important for you to immediately understand what that means. A function is going to be differentiable as long as it's continuous, smooth, no corners, and no vertical tangent lines. In other words, it's got to be a function that's got a derivative everywhere on a closed interval. And then we're told that f of a equals f of b. Then there exists a c in a to b where f prime of c is equal to 0. All right? So let's actually first just try to interpret the theorem, right? The theorem says that if we've got a differentiable function, a smooth function, right, on a closed interval, where the first y value is equal to the last y value. Actually, let me put y first and y last, right? Those are literally the first y value and the last y value. Then there's got to be an x value. How do I know it's an x value? Kind of by looking ahead, to be honest with you. There's an x value in the interval a to b where the derivative is equal to 0. All right. Now letter A says, given the graph shown below, where f of a equals f of b, draw a curve that is not a horizontal line, but is differentiable through the 2 points and show the locations where f prime of x is equal to 0. I'd like you to pause the video and do this right now. Draw any curve you want, make sure it's a function, all right, and don't make it a horizontal line. But besides that, draw a differentiable curve between point A, and point B. Now, everybody doing this video should have done a different curve, although very likely many of them are similar. All right. Here, I'm going to just draw one. Ooh, crazy. Right? Nice, smooth, and differentiable. What Rolle's theorem guarantees is that there is at least one x value where the derivative is equal to 0. Well, in my graph, apparently, there's 3 of them, right? So there's one of them right here, there's one of them right here, and there's one of them right here. Or at least, that's the best I can do in terms of tangent lines, right? So I have 3 of them. Rolle's doesn't say there has to be exactly one. There's just got to be at least one. All right. Now, the proof of this is kind of cool. All of these theorems, because they're theorems and not axioms, have formal proofs behind them, sort of cut and dry. You can't dispute these proofs. Some of them are not very illustrative or informative, but I like this one, right? Because it really illustrates how a lot of mathematicians think. All right, in order to really do this, you have to consider all cases, and there's really 2 cases. Case 1 is the function is a horizontal line, right? And that could very well be the case, right? You could just have f of x equals a. Well, maybe not a. We're using a for something else in this problem. F of x just equals a number. Let me go with a number. F of x equals 5, right? So then what you got is you got your graph that just looks like this. All right, yeah, I got a and 5, and I got b and 5, and there's my function. So of course f prime of x is 0. It's 0 everywhere, right? So that's not interesting. Okay, then the second issue is the function is not a horizontal line, right? Because those are your only 2 cases. Now, again, here's where a true mathematician would start to have beefs with me. Okay, I'm going to start throwing in some things like, well, then clearly, and obviously, and apparently, and these are really things that should be proven. But, right, just from pure experience, what we find is that if we don't have a horizontal line, there must be at least one turning point. There's got to be at least one turning point somewhere in there. Now, because the function is differentiable, f of x is differentiable, f prime of x must be equal to 0 at the turning point. Now, again, there's a lot of details that are left out of this extremely informal proof. So for the college math teacher or really hardcore kind of calculus enthusiasts, yes, I should prove why there's got to be a turning point by some kind of argument about increasing and decreasing things. I should prove why f prime of x is equal to 0 at a turning point when the function's differentiable. But again, just based on the experience that students should have in differentiable calculus up to this point, you should feel comfortable with that proof. So let's go on to an even more important theorem. I'm going to clear this out. Rolle's theorem is one you want to know. If you start and end at the same y value, there's got to be a place where the derivative is equal to 0. Here it goes. All right. The mean value theorem for derivatives, one of the most important theorems in all of mathematics. So important that you literally cite it using MVT, which is a bit confusing because earlier this year we had the IVT, which was the intermediate value theorem. This is now the mean value theorem. Anyway, it's the mean value theorem for derivatives, the MVT. Let's take a look and see if we can interpret it. This one is a little bit of a tricky one to interpret unless, of course, you already know the interpretation. Then you think it's really easy. But read it over and then see if you can figure out what the theorem is saying kind of from a graphical perspective. Okay, pause the video now. All right, let's go through it. Really would love to know how many people actually got the interpretation right, because it is a little tricky. All right, so let's take a look. It says, for a differentiable function f of x on the interval a to b, let's pause for a minute, it's differentiable. It's continuous, smooth, there's no vertical tangent lines. Okay, I'm good to go. There exists a c such that f prime of c is equal to f of b minus f of a divided by b minus a. All right, well, let's see what I can see here. All right, remember, more important than anything is trying to just figure out what in the world they're talking about. All right, let's not make Rolle's theorem apply. Let's put 2 points like this. Let's call this f of a. Let's call this f of b. And now let's just draw a generic curve between the two. Let's give it a turning point. Something like that. That looks good, right? Kind of smooth. Maybe not the prettiest thing on earth. All right, well, let's see. So there's some magic c again, and it's an x value, right? It's definitely an x value. This should look familiar. All right, and that's the real key. If you don't know what that is, then you're in trouble here. All right, so what is that? What is it? What is it? What is it? Right? Oh, I know what it is. It's the average rate of change. Something that new Common Core Algebra 1 students are going to be learning about. Common Core Algebra 1. Average rate of change of f of x over that entire interval, right? Over the interval a to b. So it's on average how fast the function is changing from a to b. And we can actually visualize what that is graphically because it's actually the slope. That is just a terribly drawn line, but okay, we'll go with it. Actually, we'll stick in red. It's the slope of that line. All right, so we know what that is. That's the slope of that line. I'm going to actually now do it in red. Right, so what does this theorem say? It says that there's got to be an x value somewhere between a and b where the tangent slope, right, because that's what this is, it's the tangent slope. The tangent slope equals the slope of the red line. That's cool. I think I see one right here. Fill that in. I think right there. Why do I think there's one right there? Because that line's parallel to that one. There's one. I wonder, maybe right about here. Why do I seem to be doing a decent job of this? Yeah, there's one I think right about there. Oh, I think there's one right about here. Yeah, there's a lot of them. Isn't that cool? The mean value theorem says that if we've got an interval, some x, y interval, or sorry, some x to x interval, so, -2 to 3, and we know that our function is differentiable, so it's smooth, right? And we have these two y values, 0, doesn't really matter. Then somewhere along the line, the average rate that the function is changing will be the same as the instantaneous rate. A lot of physics teachers like to talk about it this way. If I'm driving from here to New York City, and let's say that New York City is 100 miles away, right? 100 miles away. And let's say starting, stopping, all of that, it takes me 2 hours to get there, right? My average speed, of course, easy enough, is 50 miles per hour. All right, but what the mean value theorem, whoops, my bad. What the mean value theorem says is that at some point in time, my instantaneous speed also had to be 50 miles an hour. There's no way for me to average 50 miles per hour without at some point in time traveling 50 miles per hour. It's a really, really neat theorem. I'm going to clear the theorem away, so copy down what you need to, as if any of that's really helpful. You never know. All right, let's take a look at an application. Number 4 says, consider the function f of x equals x squared minus 2x plus 5 over the interval 2 to 6. Determine the average rate of change of f over this interval. Why don't you go ahead and do that really quick, okay? Average rate of change. All right, let's do it real fast, right? Average rate of change is change in f over change in x, if you will, f of 6 minus f of 2 divided by 6 minus 2. F of 6, you don't want to see me do that calculation, is 29. F of 2 is 5. Obviously, the denominator is 4. So 24 divided by 4 gives me 6. So my average rate of change is 6. So on average, for every 1 unit of increase in x, we're increasing y by 6 units. Just make sure you remember what it means. Letter B now asks us to find a value of c such that f prime of c is equal to the average rate of change you found in part A. Why don't you go ahead and do that? All right, let's do it. Pretty easy, actually. F prime of x, simple enough to find using the power law, right, is 2x minus 2. So if we interpret this literally, it would be 2c minus 2 is equal to 6, 2c is equal to 8, and c would be 4. In other words, again, the instantaneous rate at which this parabola or quadratic is changing at x equals 4, c equals 4, whatever, is the same as the average rate it's changing over the interval 2 to 6. May not seem obvious why that theorem's important, but it really, really is for upper level math and all sorts of physics-y stuff. It's a good word. Okay, I'm going to wipe out the text. All right, this next one's a fun problem because it's calculator based and gives you a good sense for how you have to be able to use your graphing calculator. An object travels such that its horizontal position is given by x of t equals t squared times sine t. Letter A asks us to find the average velocity of this object over the interval 1 to 6. So why don't you go ahead and do that? All right, well, my students have learned that the average velocity, okay, V average, is just a special case of average rate of change, right? It's the change in position divided by the change in time. Specifically here, it's x of 6 minus x of 1 divided by 6 minus 1. If you actually put this into your calculator, maybe you put it in as, this, then you can actually do this kind of calculation using function notation on your calculator, but whatever, at the end of the day, this is negative 2.81. Whoops, no, that was wrong. Interpose some digits there, 2.180. All right? So, letter B. How many times over the interval 1 to 6 is the velocity of the object equal to the average velocity found in A? So this is directly the mean value theorem. The mean value theorem guarantees us that the average rate of change of this function right here will be also the instantaneous rate of change of that function, which is the velocity, right, the velocity function, at least once. But this question asks, how many times does it happen? All right? Pause the video now and see if you can figure out how to do this. Keep in mind that you have your calculator. All right, so real quick, of course, what we're going to do is we're going to find the velocity function by finding dx dt, or x prime of t, however you'd like to think about it. For that, we have to use the product rule. Derivative of t squared is 2t times the sine of t plus t squared times cosine t. Now the question really is, how many times is this equal to this? The mean value theorem tells us it's going to happen at least once on the interval 1 to 6. For my students, I would want to see this. I would definitely want to see this. And then really you can just give a final answer. But let's bring up the TI-84 now to see how we're going to do it. Now, even though our function is in terms of t, we're going to work this all in function mode, not in parametric mode. All right, and we're just going to interchange x for t. So let's make sure we're in the right mode. Hit mode. Uh-oh. Let's make sure we're in function mode. I've been doing a lot of polar work lately. So function mode. Go into y equals. All right. And now what I'm going to do is I'm going to enter in, I'm just going to kind of solve this equation graphically, right? So I'm going to clear out what's in y1 and any other y's. And in y1, I'm going to put in 2x times the sine of x, watch my parentheses, plus x squared times the cosine of x. All right. Make sure that all looks right. I know that can be kind of tough on some of the TIs given their sort of scrolling that they do, but make sure it looks good. All right. In y2, I'm going to put in negative 2.180. I really like doing it this way rather than using the 0 command because I really want to see on the graph when the velocity dips down to that negative 2.180. I want to see that. I don't really want to see the zeros of some kind of equivalent equation, but that's me. All right, let's go into our window and think about how we need to set this. Now, the beautiful thing is that the problem has actually given us the window. We want to set x min to be 1 and x max to be 6. We don't want any other values than that. Because if we open it up farther, we very well may see intersection points that shouldn't count or that we don't want to count. All right? So x min is going to be 1. X max is going to be 6. Change anything else you need to. Now y min, y max, well, all I really know is that I want to be able to see a y value of negative 2.180. So I'm thinking I'm going to go y min is negative 5. Y max is 5. All right. And now hit graph. By the way, if you're not getting a graph that looks like mine, it very well could be that you've entered the equation wrong, or it could be that you're in degree mode instead of radian mode. Remember, anytime that we're working calculus, we have to be in radian mode, or the derivative of sine is not cosine. So it's kind of cool, right? I mean, you can see on that graph, you can definitely see the intersection points, you know, there and there. So it's easy enough, right? There are 2 intersections, so it happens twice. Mean value theorem guarantees it'll happen at least once. The average rate of change has to occur once as the instantaneous rate of change, one or more times, as long as the function is differentiable. All right, I'm going to clear this out. Great. The first lesson in Unit 11 is done. We're counting them down, folks. We're near the end of the course. In the next lesson, we're going to review how to find absolute maximums and minimums, and that's going to launch us into then a lesson investigation of the process of optimization, one of the, I think, most fun and interesting applications of differential calculus. All right, but that'll have to wait. For now, let me just remind you, this has been another Arlington High School Math 4 Honors lesson. I'm Kurt Weiler, and until next time, keep thinking, keep solving problems.